Delighted that you are here for our first inaugural science event in our Science for Seminary program. We're very excited about this. We're very much thinking this science engagement is going to be vitally important for theological education. You know, people of faith encounter science every day. And in the pews of your congregations are science teachers, scientists. How do the people in the pews integrate what they're learning from science with the faith tradition? That is why we are up to this. Theological education today needs to engage science. That is not optional, it's essential. Pastors must be able to engage and to help integrate this for their people and with their people. This initiative is consistent with McCormick Seminary's commitment to prepare women and men for ministry that is effective, faithful, and relevant to our contemporary context. That is why we think this is so very important. Our grant from AAAS and the Association for Theological Schools has made it possible for us to go deeper in this commitment. A few notes for the evening. You may think you're hearing voices. You are. It's not students whispering over in the corner. There is an intentionality in this booth right here. I want to tell you about that. Those of you that know McCormick know of our commitment to cross-cultural education. Well, we are very pleased to be able to bring this program tonight in bilingual form. We have it in English and simultaneous translation. And by the way, if anyone else would like the earphones, you can hear this in Spanish. Well, welcome to these. Just raise a hand and we'll get them to you.
Si alguien desea oír esto en español, todavía tenemos material disponible, equipo disponible.
Awesome. Thank you.
Anna, could you just speak a little bit louder?
A little louder, I can do that.
Thank you.
So there are just a few standing in the back, and there may be some more coming in from the reception. As more folks come in, please signal if the seat's open near you, signal and let them come by. There are even a couple of seats on the front row. Remarkable, yes. You never have that happen in church, right? Seats to fill up. Well, let's see. One other note. You found a index card in your seat and you're wondering what that's for. That is us looking ahead to the interaction we'll have with our speaker tonight, and we're wanting some good questions to come from you all. So if you feel a question coming on during the presentation, please write it down legibly, and that will be passed to the center of the room. The ones on this side are going to be collected by Reggie, who is my co-leader of the Science for Seminaries project. And he will collect from the west side, and from the east side, affiliate faculty member Linda Eastwood, and our own resident scientist theologian will collect from the east side. And they'll sort through those at the end and find really good questions. And I want probably all good questions. It's a question of how many we can take in one night. So we'll begin with what you select. And students, we especially want questions from students. If you are a student, put a little star on your card, and we will make sure that that gets attention. Well, those few notes, and then I want to invite President David Crawford forward. First a word. I want to tell you how very supportive he has been of this project. From the very beginning, he helped us write the proposal and has been an enthusiastic supporter of it all along. And he wishes to bring you greetings.
Thank you, Anna. Good evening. Good evening. On behalf of our board chair, Mr. Pete Cochran, who joins us here tonight, our vice chair, Connie Lindsay, our board, trustee, in fact, one who has joined us tonight, Bob Unlove, and his wife Nancy. On behalf of the amazing faculty at this wonderful school, our students and our staff, it is my honor to welcome you all to the McCormick Theological Seminary. You all are in for a real treat tonight. Before we begin, I want to take a moment to thank all of the great people here at McCormick who make these events happen. They don't just sort of happen without a whole lot of work. And you see some of those people, and you probably saw more of them than usual because we were shifting between two very, very exciting events tonight. And I want to mention one guy in particular, because if it weren't for him, we wouldn't have chairs to sit on and tables. Armando Del Valle, who makes all this happen and did this turn in about 30 minutes. Who was the coordinator of this. You probably made your RSVPs through her. She has helped coordinate this from the beginning and just done a wonderful job. So thank you for your help and support on this event. We did an amazing Tracy Turner, and I don't know if she's in here, but the only way we eat or drink anything around here is with Tracy's restaurant. So Tracy, please, wherever you are, thank you for everything you do for us. And I want to thank Professors Anna Case Winters and Reggie Williams, two extraordinary scholars and two extraordinary human beings. It is an honor to work with you each and every day. Friends, and many of you know, because you may have been here, just came from another extraordinary event in this very room, in which we welcomed the Reverend Dr. Otis Moss III, named one of the 12 most effective preachers in the English-speaking world by Baylor University's Truett Theological Seminary, and civil rights icon Reverend Jesse Jackson. Now think about these two events happening back-to-back in this building, in this very room, a conversation with two gifted pastors, both the product of formation at a seminary like this one. Two national leaders having a conversation about how we, as human beings, live faithfully together in community, combating the evils of violence, income inequality, and destruction of our planet's resources. Shift to this, a conversation about extraterrestrial life in an interactive cosmos. If you think a minute, these two conversations are connected. Connected by a human desire to create a more perfect world and to understand more fully our place in this bigger, greater thing that swirls infinitely around us. Friends, we are grateful to the American Association for the Advancement of Science for their support of our work and for making this very special evening possible. Thank you all again, and welcome.
The great pleasure of introducing Grace Wolf Chase. She is an affiliated member of the Zygon Institute for Religion and Science. She is vice president of the Center for Advanced Study in Religion and Science. Her work integrates academic research. Her work is in star formation. She integrates that with public education in science, events like this, and also engaging citizen science and people around the world in science. She holds a baccalaureate degree in physics from Cornell and a PhD from the University of Arizona. Dr. Wolf Chase is also a lifelong Lutheran and understands her work as a scientist in terms of vocation. And I think we'll want to hear about that as well. I've heard her speak, and you are in for a fascinating presentation. We are privileged to have Dr. Grace Wolf Chase with us tonight.
Thank you, Anna. Thank you very much. In fact, I want to start by expressing my thanks to Anna and Reggie and Linda and all of the wonderful work you're doing integrating science into the seminary program here. I also want to thank my Adler colleagues for coming tonight, Aubrey and Dana, and my son Jason, who's here to support me as well. So let me just start by telling you a little bit about what astronomy is these days. Astronomy incorporates virtually every field of science you can think of. Cosmology, the study of basically the large-scale structure and evolution of our universe. Astronomy is astrophysics, astrochemistry, astrobiology, planetary science. My own research, as Anna told you, focuses and has focused for decades on trying to understand how stars and planets form in the universe today. I've also been involved in dialogue between scientists and theologians who are interested in creative mutual interactions for about 20 years now. I don't know if Carol and John Albright are in the audience right now, but they sort of got me started in this about 20 years ago. Now, I wouldn't presume to practice theology without a license, as my friend, Lutheran theologian Ted Peters might put it, but I do hope to offer you some insights tonight from science that I think are worthy of theological and ethical reflection. I love this quote by British writer Sarah Maitland. I think it's very appropriate for tonight. "Natural history is not taught in seminary." But now it is. This is curious, as most people in pastoral ministry are about 567 times more likely to be asked about cosmology or subnuclear physics or human biology or evolution than they are to be asked about irregular Greek verbs or the danger of the Patripassianist heresy. I don't know where the number 567 comes from, but kudos to McCormick and to all you young seminarians. I know as a scientist, if anybody asked me about the Patripassianist heresy, they'd get a very blank stare. So I'd like to start on a theme that I think is sort of at the root of both religion and science, and I offer some quotes both from scripture and also from prominent scientists. So awe and wonder in religion. These are some of my favorite passages from the Hebrew scriptures. Psalm 8. "When I look at your heavens, the work of your fingers, the moon and the stars that you have established, what are human beings that you are mindful of them, mortals that you care for them?" And from Job, "Can you bind the chains of the Pleiades or loose the cords of Orion? Do you know the ordinances of the heavens? Can you establish their rule on the earth?" Abraham Joshua Heschel, in God in Search of Man, a Philosophy of Judaism, writes, "The surest way to suppress our ability to understand the meaning of God and the importance of worship is to take things for granted. Indifference to the sublime wonder of living is the root of sin." Theologian Michael Yaconelli, in Dangerous Wonder, expresses a similar view, where he expresses the view that the most critical issue facing Christianity today aren't on all those controversial issues that divide people within a denomination as well as across different religious traditions. No, he says the most dangerous thing these days, the most critical issue is dullness within the church. We have lost our astonishment. He goes on to say that the church should be full of Christians who seek questions rather than answers, mystery instead of solutions, wonder instead of explanations. And I would venture to predict here that if we could recapture that wonder and awe in our churches, we might repopulate some of our pews. Expressing very similar kinds of sentiments, I offer several quotes from very prominent, notable scientists. Stephen Hawking, "What is it that breathes fire into the equations and makes a universe for them to describe? The usual approach of science constructing a mathematical model cannot answer questions of why there should be a universe for the model to describe. Why does the universe go to all the bother of existing?" Freeman Dyson, "It is true that we emerged in the universe by chance, but the idea of chance itself is only a cover for our ignorance. I do not feel like an alien in this universe. The more I examine the universe and the details of its architecture, the more evidence I find that the universe, in some sense, must have known that we were coming. Albert Einstein, all religions, arts, and sciences are branches of the same tree. All these aspirations are directed toward ennobling man's life, lifting it from the sphere of mere physical existence, and leading the individual towards freedom. And another Nobel Prize winner in physics, Arthur Schawlow, it seems to me that when confronted with the marvels of life and the universe, one must ask why and not just how. The only possible answers are religious. I find a need for God in the universe and in my own life. So, tonight, after a very quick look at the nature of science and an exciting new branch of theology called astrotheology, I want to take you all on a brief tour of the universe in space and time, introduce you to some of its contents. This will be necessarily brief, but hopefully those of you who have not had any sort of a background in astronomy will benefit from this. And then I'd like to morph into talking about the impact that science has had in some of the ways we think about God, and how what we've been learning over the past few decades in science informs our thinking on the prospects for the existence of extraterrestrial life. And then we'll end with some reflections and open questions. So what is science? My colleagues and I absolutely loved this quote from Matt Damon in The Martian. I'm going to have to science the expletive out of this. Why did we love it? Because it uses science as a verb and turns science into the process that it is, rather than a boring, dull collection of facts. So science has been a remarkably useful tool for solving problems. However, it's also a very successful instrument for exploring the nature, origin, and evolution of the cosmos itself. Now, some of you may be familiar with this gentleman here, retired physicist and Anglican minister, John Polkinghorne, who coined this catchy phrase, epistemology models ontology. And since this is very obscure to a lot of people, we will, in the tradition of Martin Luther's Small Catechism, we'll ask, what does this mean? For our intents and purposes tonight, what it means is that scientists are critical realists, and we believe that what we learn through science does reflect reality. It reflects something about what the universe truly is like. I want to note that what we call science today is a relatively recent development in human history. The term scientist was only coined in about the year 1830. And the methods we use to test hypotheses through observations and experiments that we use to develop theories that make actual testable predictions about the universe. These theories are based on many observations and experiments, and good theories are always consistent with what we know from other branches of science. So this methodical way of exploring the universe is very young when we look at the history of human civilization. Now, the material for tonight's talk, I want to actually promote two books. Some of the material for tonight's talk is taken from these books, as well as from an article I wrote for Theology and Science that's a response to one of these books. The books are called Interactive World, Interactive God, and Astrotheology, Science and Theology Meet Extraterrestrial Life. So the interactive book is actually a compilation of essays by scientists, theologians, and philosophers that reflect on the fact that across all branches of science, it seems that there's one concept above all that's emerging as fundamental to everything that we study, and that's the concept of interactivity as a fundamental property of the universe. So that book, I highly recommend it. I am one of the chapter authors. The book Astrotheology is a wonderful exploration of this new branch of theology. I wrote a response to this called New Worlds, New Civilizations, From Science Fiction to Science Fact, that I also invite you to check out. Ted Peters, who is a Lutheran theologian, edited this book, and I'm going to read you his definition of astrotheology. Astrotheology is that branch of theology which provides a critical analysis of the contemporary space sciences combined with an explication of classic doctrines such as creation and Christology for the purpose of constructing a comprehensive and meaningful understanding of our human situation within an astonishingly immense cosmos. So let's take a look, a journey through the universe, and get a sense of just how astonishingly immense the cosmos is. How many of you, in addition to me, are actually old enough to remember when this photo was taken? Show of hands. I don't expect any of the young seminarians, but there are some hands here. Okay, yeah. We are celebrating the moon at the Adler Planetarium this year, and I hope that everyone here gets a chance to see the new show, Imagine the Moon. It is a wonderful exploration of science, of culture, of art, and I think whether you remember photos like this or not, you will love this show. The moon is our nearest natural neighbor in space at a distance of about 250,000 miles. As I love to tell people living in Naperville, commuting to the city every day for 20 years, I have more than commuted this distance. However, we're going to go out to a much larger distance very quickly here. So this is the dimmest slide, so I apologize if people have trouble reading it. The details really aren't all that important. What you're looking at here is our solar system, the sun and all the worlds that orbit the sun, or some of the worlds that orbit the sun. I use the word worlds because not just planets orbit the sun. We have dwarf planets and comets and asteroids and a lot of worlds that come in various different shapes and sizes. Now, I want you to know that the scale of the solar system, roughly 10 billion miles across. The distance between the sun and the earth, right here, roughly 93 million miles, and it takes light about 8 minutes to travel that distance. So this is something I want you to think about throughout this presentation. We never see the universe as it is today. We're always looking into the past. And the further out we look, the further into the past we're looking. This is what we call the solar interstellar neighborhood. Not all the stars near our sun, some of the brighter ones. So now we're at a scale not of billions of miles, but tens of trillions of miles. 1 light year is approximately 6 trillion miles. And this represents about 30 light years across. Now I want to say something about stars. Our sun is a star. Stars come in different colors, temperatures, sizes, masses, how much stuff they contain, how bright they are. And for most of their lifetimes, like our sun, they fuse lighter elements, hydrogen primarily, into heavier elements, helium primarily, at the cores, at the tremendous temperatures and pressures at the cores of these stars. They're nuclear furnaces. Now, about 70% of all the stars are stars we call red dwarfs that are intrinsically maybe 100,000 times fainter than our sun. And when I say intrinsically, I mean if we could compare them at the same distance. That's really important because the sun is so much closer than all the other stars. But they're interesting because they're so ubiquitous. 50 of the 70 nearest stars are red dwarfs, but you can't see any of them because they're so dim. You need special instruments, telescopes, to be able to see them. At the other end of the spectrum, we have bright, luminous blue stars that can be hundreds of thousands of times brighter than our sun. These stars are so hot and they have such great pressure at their cores that through their lifetime, they fuse elements as heavy as iron. And once they have iron cores, they explode into what we call supernovae. And they enrich space with the heavy elements that are in all of our bodies today were produced in the cores of giant stars long ago. So that's an introduction. I do want to mention the closest star to our sun, Alpha Centauri, is actually a double star, and there's a nearby star that's even closer to our sun called Proxima Centauri. That star is orbited by a planet in a potentially habitable zone. So there's a potentially habitable planet in the nearest star to our sun. On somewhat larger scales, we go out to the size of our Milky Way galaxy. Our sun is one of the roughly 400 billion stars in the Milky Way galaxy. This is how we see our galaxy. Our galaxy is about 100,000 let me try that again. 100,000 light years in diameter, which comes out to be about 600 quadrillion miles. So clearly we don't travel through our galaxy. We don't see it like this. We make measurements from within our galaxy to infer that our galaxy has this nice, pretty spiral shape. And our sun is located out here in the suburbs, about halfway out from the center of the galaxy. Again, we never capture now. It takes light 100,000 years to traverse the diameter of our galaxy. Going out to the local galactic group, and yes, local has very different meanings in astronomy from what it has to most of us. Now we're on a scale of about 6 million light years across. The two largest galaxies in the local group are the Milky Way and Andromeda. They're approaching each other, and in roughly 4 billion years or so, they should merge through their mutual gravity. And notice I say merge and not collide. That's because a typical star is about 1 million miles in diameter, but the typical distance between stars, tens of trillions of miles. So sizes of stars are very, very small compared to the distance between stars. So on even larger scales, galaxies are arranged in these beautiful, large, incomprehensibly large filamentary structures that are shaped by gravity called superclusters. Going out to the largest observable scale, and yes, this is a very quick, brief tour here. This particular diagram isn't meant to show you any particular features of our universe, just to underscore the fact that we have a horizon in our universe beyond which we cannot explore. Now, those of you who have heard that the universe is approximately 13.8 billion years old may be wondering right now how the observable universe, the diameter of our observable universe, is over 90 billion light years across. That's because something interesting has been happening over the past 13.8 billion years. Our universe has been expanding. When I say a galaxy is 10 billion light years away, what I really mean is the light from that galaxy started on its journey to us 10 billion years ago, when the universe was smaller, when galaxies were closer together than they are today. A note here, there are many more stars in the observable universe than there are grains of sand on the Earth. So we'll return to that expansion concept in a few minutes here. So we've gone sort of on a whirlwind tour through space. Now let's go on a whirlwind tour through history, big history here. This is a common visual tool for thinking about the history of our universe, where we compress 13.8 billion years onto one cosmic year. It's called the cosmic calendar. On this scale, 1 second is about 500 years. And this big history is accessible to us because information doesn't travel faster than the speed of light, and because we live in an expanding universe with a finite beginning. We can look out at great distances and actually see our universe changing in time. The implications of this are profound. A few things to note here. On this scale, our Milky Way galaxy doesn't form until more than a third of the way into the cosmic year. Our sun is a third-generation star that doesn't form until more than 2/3 of the way into the cosmic year. And most of the interesting things in human civilization actually occur in the last minute, the countdown to midnight on December 31st on this calendar. So science as we currently practice it, really arose during the Renaissance. So for the benefit of the people who can't read the slide here, I'm detailing some things about the Renaissance scholar, Leonardo da Vinci, who basically did everything. Painter, sculptor, architect, mathematician, engineer, scientist. Today we can't even begin to be proficient in one of these fields, let alone all of them. Only 500 million people on Earth 500 years ago. Now there are over 7 billion people on Earth, and by the middle of the century, probably over 9 billion people. So this is actually, I want to stop here and make the point that science is recent, and this is why it really doesn't make sense to try to map our views of the cosmos today on the way people thought about the cosmos thousands of years ago. So briefly, I'm not teaching the history of science here, but I do want to go through a few big shifts in the way we thought about the structure of the universe. So thousands of years ago, in the ancient Near East, their cosmology, they pictured the Earth sort of like the universe, the cosmos, as three-tiered. You had Sheol, the abode of the dead, below the Earth, the waters, which fell to the Earth when it rained, did that when the floodgates were opened in a vast dome, kind of like a planetarium. So here we have their concept of the stars and other things in the night sky as being very close to us. And the waters were above the stars and this firmament. Now, at the time of Jesus, for example, this picture had already been replaced with a different view of the cosmos. Now, there are various models that have the Earth at the center of the universe and the planets orbiting the Earth. I don't want to go into this model in great detail, but you'll see here the planets, the stars are further out than the planets. And these worlds were considered to be different from the Earth. Not really worlds. The planets were called the wandering stars because they moved differently from the stars in the night sky. So by the time of Copernicus, during the Middle Ages, during the Renaissance, the Earth-centered view started to become replaced with thinking about the sun at the center of our solar system. And this actually made the orbits a little easier to understand mathematically. It was a model with no observational support at the time. It wasn't until Galileo, the invention of the telescope, and other tools that allowed us to probe further into the universe that this model became generally accepted. So today, we think of the universe without a center. Now, I want to note something very important. None of these previous models are in any way, shape, or form stupid. They start with very common sense ways based on observations that were possible at the time. And as I mentioned, the Copernican view was not automatically accepted. There was no observational evidence. So now I want to shift from our brief tour in space and time to the way science has impacted the way we think about God. So in the 17th and 18th century, our view of nature was the universe was something of a big mechanism, was understood that way. In Newton's view, space is kind of like an empty stage that provides this absolute frame of reference. And the cosmos is populated by things, like a big cosmic play. The material world behaves strictly in terms of cause and effect. Newton envisioned gravity as a force acting between different large bodies, like the Earth and the Moon, for example. Now, this actually affected the way people thought about God. And that makes sense because throughout the centuries, philosophy and more recently science has influenced the way people think about God. My good friend, Brother Guy Consolmagno of the Vatican Observatory, has remarked that one might reasonably expect a creation to reflect the personality of the Creator. And of course, in Christian traditions, We think of God as creator and sustainer of all that is, which includes material reality. So in Newton's time, the universe was envisioned as this large mechanism, which ultimately led to thinking about God in ways that were not very compatible with tradition, at least with traditional Christian theology. It led to what we call God of the gaps theology. There are those of you in the audience much more familiar with this than I am, I'm sure. But basically, God as an explanation with a capital E competed with scientific explanations, so that people looked at things in terms of either we've explained this mechanically or God did it directly. So God becomes yet another material cause whose role becomes smaller and smaller as our scientific understanding grows. And the ultimate expression of this, which was a very popular view in the 17th and 18th century, is deism, where God basically becomes the initial cause of the universe and then hands off, leaves things alone. Our understanding today, that picture doesn't fit our contemporary understanding very well at all. So the universe today seems much better described as an interacting web of relationships than a collection of things. There are two 20th century branches of physics that really revolutionized our understanding of the universe. Quantum mechanics, which describes interactions at the levels of atoms and subatomic particles, and general relativity, which describes interactions that govern the large-scale structure and evolution of the universe. Don't worry, I'm not teaching quantum and general relativity tonight. I'm just going to show you a couple of examples at how these branches of physics have been invaluable for us to further our understanding of the universe. In the decades that I've been a scientist, more and more frequently I have heard metaphors from biology applied to the universe. Especially in my field, when we talk about nature and nurture, birth and death in the context of the formation of stars and planets. So we'll come back to that in just a little bit. In the 19th century, astronomy became more than just how things move in space. This gentleman here, with a nice little double entendre on the word father, is sometimes referred to as the father of astrophysics. Father Angelo Secchi built a spectroscope and used it to study the spectra. A spectroscope is a device that spreads light out into its component colors. Used it to study the spectra and classify the spectra of different kinds of stars. And you'll note there are all these dark lines in the spectra here, and they're different for different types of stars. Well, at the time, in the 19th century, Angelo Secchi did not have a theoretical framework to understand how these lines are produced, but he did know it related to composition. So a shift happens in the late 19th century. Astronomy becomes astrophysics, becomes using physics to actually study what things are made of. This woman here, Cecilia Payne-Gaposchkin, in the early 20th century, did her dissertation also on the spectra of stars. She is the person who first proposed that that stars are mostly hydrogen. And her dissertation has sometimes, by some prominent scientists, been referred to as the most brilliant dissertation in astronomy in the 20th century. She related the spectra not just to the composition of stars, but also to their temperature. So at this point in time, we start to understand how we can apply quantum mechanics to the interactions between light and matter, how light and matter interact. Now, some of you have been to a clergy day at the Adler Planetarium. I don't know how many of you have, but I have a bunch of posters in my office. Aubrey knows this, that highlight clergy who have made especially significant contributions to the field of astronomy. And Angelo Secchi is among those clergy. So I want to shift now from quantum mechanics to general relativity and how that's impacted our thinking about the universe. So in 1915, Albert Einstein formulated what's known as the general theory of relativity, and it brings with it a radically different understanding of space and time. Now, before I tell you about this, let me emphatically note that Einstein didn't overthrow Newton. Newton's description of gravity works perfectly well in ordinary circumstances, as do Newton's laws of motion. But on scales that are very much outside of human experience, where there's a lot of gravity, really massive objects, large-scale distances in the universe, we need a different mathematical description of nature. And in Einstein's view, we don't have space and time as separate entities. But what we have is something that behaves almost like a fabric, space-time. They're intimately connected. Einstein didn't like the idea of action at a distance. He referred to that as spooky. And in Einstein's view, there is this intimate connection between matter and gravity, which is in the nature of space-time. The physicist John Archibald Wheeler puts this beautifully. Space-time tells matter how to move, and matter tells space-time how to curve. And if this graphic isn't that much to your liking or isn't very familiar enough, maybe you'll like this one. So, if you've got a cat at home, you can relate to this. So, general relativity has been one of the most successful theories in physics. It's made many testable predictions. One of the predictions of general relativity is that space-time should expand, increasing the distance between galaxies over time. Now, the astronomer Edwin Hubble conducted observations that illustrated this expansion, that galaxies that are more distant appear to be moving away from us faster than galaxies that are close by, which is exactly what you should observe if space-time is expanding. Hubble did those observations, you might be interested to know, with the help of a janitor to become astronomer's assistant named Milton Humason, who was very important in making these observations as well. Now, another interesting historical note is that actually this gentleman here, Father Georges Lemaitre, published a solution to Einstein's equations of general relativity for an expanding universe 2 years before Hubble's classic paper, only he published it in an obscure Belgian journal. 2 years after Hubble's paper, in 1931, the equations that describe this expansion had been removed. Lemaitre did that himself because he felt his observations were not good enough, were not strong enough to validate his discovery. So Father Lemaitre is known as the father of the Big Bang, that earned him this title. And I find it really ironic here. So as many of you probably know, there are a lot of people, a lot of religious people that refer to the Big Bang Theory as atheistic. Well, at the time that Lemaitre proposed this, he encountered the opposite view. He encountered scientists who told him that his Catholic faith was influencing his view on the universe. The fact that the universe actually has a beginning was actually the reason why he liked the Big Bang Theory, or Big Bang Theory. Whenever I say that, I think of the comedy, I'm sorry. Lemaitre's response to that suggestion is really, really interesting. He says, as far as I can see, such a theory remains entirely outside any metaphysical or religious question. It leaves the materialist free to deny any transcendental being. For the believer, it removes any attempt at familiarity with God. It is consonant with Isaiah speaking of the hidden God, hidden even in the beginning of the universe. This is something of an ultimate rejection of any kind of God of the gaps theology. In Lemaitre's view, the universe doesn't need to have a beginning to be utterly dependent upon God. The emphasis on a beginning reflects our linear thinking and experience of time within the universe. Important note here, the Big Bang is not an explosion that happens in space that's already there, that sends shrapnel in the form of matter through the universe. Space-time itself has its origin in what we refer to as the Big Bang. The Big Bang is kind of a misnomer, as many things are in many areas of science. So, of course, Father Lemaitre is one of our poster clergy as well. Now, the last prediction of general relativity that was verified just a few years ago was the prediction of gravitational waves. And here, you see what's going on here. So the motion of very, very massive objects in space send out ripples in space-time. And I know how science fiction-y that sounds, and I apologize to the translator because I'm sure that science fiction-y is not a word. But this is actually science. The Laser Interferometer Gravitational Wave Observatory has been detecting gravitational waves for several years now, for a few years. And in the next, whoops, let me go back here. Oh, come on, do your thing. Let me try this once more. There we go. No, the punch wasn't spiked. You're really seeing the Earth compressing and expanding here. So this is greatly exaggerated, but this in essence is what LIGO detected, the Earth being compressed and expanded by the width of about an atomic nucleus. And this is why it took 100 years after Einstein formulated the general relativity to have the technology to actually make this observation. I want to note that this observation was made possible through the efforts of a great many people. So I think too often we learn in the schools, we think that all of science stands on the back of a few brilliant individuals. There are brilliant individuals for sure, but science is a community effort. The community responsible for the development of this incredible instrument and this detection, thousands of scientists around the world, in addition to engineers, technicians, educators. Very, very large collaboration. Even bigger collaborations are going on today by asking citizen scientists, people from all walks of life around the world, to help us address some very big questions by lending us their eyes and in some cases ears to help us mine information from large quantities of data. I mentioned that. I wish I had more time to talk about this. I don't. We have to move along here, but I do want to draw your attention to, I have some materials from the Zooniverse, which is a web platform that we maintain, the Adler Planetarium and Oxford University. And it's a way that you can participate in almost any research that stimulates your imagination. Sciences, humanities, check it out before you go. Definitely take one of these. So we come to nature and nurture. Astronomy is typically called a theory-driven science, and we just saw a great example of that. The prediction of gravitational waves happened way before we had the technology to actually detect them. Here's another example of where the idea preceded what we were able to observe. So back in the 18th century, Immanuel Kant and Pierre Laplace proposed what they called the nebular hypothesis. And the idea here was that our solar system might have started out from a huge cloud of matter, spinning matter in space, that was pulled together by gravity. And because it was spinning, it flattened out. And at the center, where the material was spinning the slowest, the sun formed. And then out in an extended, what we would call today, a protoplanetary disk, the planets formed over time. And this model explained a couple of observational features, namely that the planets lie more or less in a plane in our solar system, and they orbit the sun in the same direction. But of course, it was just that. It was a neat idea. There was no way to test this hypothesis. Today, we still can't run time backwards. What we can do is we can look out into the universe for examples of where similar processes are occurring today. And one of the things that we have learned in time is that the broad details, gravity is important, but today we know that stars don't form in isolation, but they form with many siblings, if you will. The nearest stellar nursery, the nearest cluster of very, very young stars that include those luminous blue stars that I was telling you a little bit about earlier on, can be found in the Orion Nebula, in beautiful winter constellation of the Orion. The nebula is at a distance of about 1,300 light years, and it contains a cluster of thousands of stars. Here is a Hubble Space Telescope view from the 1990s of the center part. The nebula itself is very hot gas that's lit up by the brightest stars in this cluster. But in the foreground here, all these little pullouts, all these little dark objects here, have been greatly studied over the past 25 years, and we have good evidence that these are planetary systems in the process of forming. The types of stars and planetary systems that form in an environment like this depend upon a wonderful array of different processes. Yes, gravity is important, but we have radiation and turbulence and magnetic fields. Star formation is what we call a very stochastic process. It's not possible to predict exactly what's going to come out from what goes in. We have evidence that our own sun formed in the company of massive stars, that one or more star exploded as our planetary system was formed. But this process plays out over an enormous range of scales and times. Just as siblings compete for food at the dinner table, stars compete to gain mass in very, very young clusters. Regions like the Orion Nebula are bright. You can see them in visible light. Where do they start out? They start out in the cold, dark places in our Milky Way galaxy. How many people see the Milky Way like this in the night sky anymore? I wanted to mention that in my first slide, that those beautiful passages from the Psalms and Job were inspired when people could look up and literally see thousands of stars in the night sky. We sadly don't experience that anymore. However, we have some compensation. This is what we call a representative color view towards the center of our galaxy in the direction of the constellation Sagittarius. Pretty much everything that's dark visibly is bright in infrared light. And I just wanted to highlight what you see here, this fluffy stuff that is colored in red and green. We can do spectroscopy with infrared and radio telescopes like you can do spectroscopy with optical telescopes. And we can identify many complex molecules in the interstellar medium, the space between the stars. These molecules lie in what we call giant molecular clouds, including complex molecules, complex chains of hydrogen and carbon molecules, hydrocarbons, that are the stuff of organic chemistry on Earth. Over the years, studying these protoplanetary disks, I'm showing you two other images that may not be completely obvious what they are. The one on the left was taken with an array of radio telescopes in Chile just this year. And basically, that radio telescope was able to study gas motions within a protoplanetary disk that point to the formation of 3 large planets in that disk. Over here, this is actually visible light, but not visible light over all colors. A particular kind of visible light, we call this a spectral line of hydrogen called H-alpha, reddish light. And the European Southern Observatory studied the formation of a planet in this very, very young system using a device called a coronagraph. You see a big hole here. That's where the star actually is. They used the technique to blot out the light from the star so you could see fainter things near the star. And then down here, these are artists' conceptions of different planetary systems that are forming. So one of the things that we've learned is that stars form with planets. We've learned this really just over the past 25 years or so. And at the same time, over the past 25 years, we've been doing surveys to find planets, we call them exoplanets, orbiting mature stars. So I want you to think about this. We have two different approaches in astronomy that are both giving us the same sort of results. We're learning that stars and planets form together And we're learning that it's beginning to look like just about every star out there is accompanied with planets. This is a chart that charts discoveries. I cannot go over all of these techniques that are used to identify exoplanets. The most prolific one has been the transit method. That's the easiest to explain. In a small fraction of cases, if a star is orbited by planets, the planets will orbit so that they actually cross the face of the star as seen from Earth. And the planets will cause a slight dip in the light that we record from that star. And you might not think you can get much information out of that, but you'll see in a few minutes we get a lot of information about the planets from that. Now, the diversity of worlds being discovered, this is out of science fiction, folks. We've discovered huge planets that orbit their stars in a few days. We've discovered mini planetary systems where you've got 6 or 7 planets that are tightly in orbit around these little red dwarf stars. We have planets that orbit 2 or more stars. Tatooine, right? We have planets in all sorts of different environments, and something like a third of all the planets that have been discovered are planets that are roughly the size of Earth or a little bit bigger. A class of planets we call super-Earths or super Terran planets. Planets that are particularly interesting targets for the search for extraterrestrial life. So, star formation studies and exoplanet studies are telling the same story. We now think, uh-oh, my goodness, this is not good. Okay, sorry, just a little hiccup. We now think there could be more planets than there are stars in the observable universe. And there are roughly 10 million quadrillion stars in the observable universe. That's a number with 22 zeros following it. This is sort of a rough breakdown of the planets that have been discovered in terms of size. And a note here again, in our solar system, at present, we don't know of any planets that fall in this size category. The Earth is the largest of the terrestrial or rocky planets, and then you have planets like the size of Neptune and Jupiter, etc. But a very common type of world appears to be worlds that are just slightly bigger than Earth. And a lot of these planets may be rocky planets that have oceans, for example. We don't know that yet, but that's been one of the ideas proposed, this particular size of planet. The Planetary Habitability Lab at Puerto Rico at Arecibo maintains a list of potentially habitable exoplanets. Now here's an important cautionary note. Potentially habitable does not mean inhabited. It doesn't even equate automatically to habitable. It means at this point in time, these worlds seem to be the right size at the right distance from their stars where they might support things like liquid water essential to life as we know it. We have a mission that, I hope, please God, launches finally in 2021 called the James Webb Space Telescope, that is going to be able to use a technique called transit spectroscopy to study the atmospheres of some of the nearer exoplanets. And in particular, this really neat system here, TRAPPIST-1, red dwarf star, 7 Earth-sized planets, 6 of them also sort of Earth mass, so they are rocky terrestrial worlds. They would fit well within the orbit of Mercury in our own solar system. Here's something out of science fiction. From the surface of any of these planets, you could see surface features on the other worlds. They orbit in such a tight orbit. This star is cool and dim, about 100,000 times cooler or dimmer than our sun. 3 of the planets that orbit this star may actually lie in the habitable zone. And the system lies at a mere distance of 39 light years. So this is one of the early targets for James Webb. So I'm going to summarize some of the things we've learned. The universe continually changes via the interaction of its parts. Stars and planetary systems form together through a delicate interplay of cosmic processes. Stars cook up the heavy elements needed for life, needed for organic chemistry in life. Complex organic molecules, the building blocks of life, pervade interstellar space. They're all over the place. The diversity of exoplanetary systems that we're discovering really rivals the imagination of science fiction writers decades ago. We know that life continually interacts with its environment here on Earth and exists in almost every niche. Now, we don't know about life elsewhere yet, but if we were to discover traces of extraterrestrial life somewhere in our solar system or in a nearby planetary system, that would be a pretty good indication that life is probably very common throughout our universe. So, on to some reflections and questions. Another quote here. I love quotes. One of my heroes, the late neurologist Oliver Sacks. The brain is the most incredible thing in the universe. If you're beginning to feel small right now, bear in mind that human beings at least have the capability of appreciating the size and beauty and vastness of the universe. Theologians have picked up on the property of the universe, that the universe is a very fertile place. It's brought forth incredible diversity, and some theologians have developed this idea to talk about how creation might both reflect and participate in God's creativity. So I know Anna is familiar with the concept of created co-creator. George Coyne, the former director of the Vatican Observatory, has really explored this idea of the universe being a very fertile place as well. The universe displays a vast, intricate network of relationships of which we are a part. A part of, not a part from. I just find this really interesting. Again, I'm not a theologian, but one of the ideas in Christian theology that tends to perplex people from other faiths is the whole idea of the Trinity, right? The fact that the way we articulate God as a relationship in Trinitarian theology. And that's kind of interesting, in my mind anyway, that this idea that relationship is fundamental to the way we speak about God. Is there harmony here? Is there something to explore? You decide. In addition to the theological questions that maybe the science can speak to, there are a lot of ethical questions that are raised by science. So we are on the verge of sending human beings to other worlds, not just the lifeless moon, but worlds like Mars that may still harbor life. How should we regard extraterrestrial life? This has to be a big conversation, right? This doesn't just affect us, it doesn't affect Christians, it doesn't affect scientists, or it doesn't just affect Christians or scientists, it affects everybody on Earth. A related question is how we should explore in a manner that is equitable to all. I have a colleague at the Adler Planetarium who spent a year at the Library of Congress researching the ethics of space exploration. And she coined this provocative phrase of decolonizing Mars to underscore the fact that in the past, colonialization has benefited some and been horrible for others. So how should we think about leaving our world? Very important questions that need to be addressed throughout different cultures around the world. I was really pleased to be a speaker at the Parliament of the World's Religions in Toronto in 2018, and it was amazing and heartening to discover that really what binds us across different traditions around the world is much stronger, I think, than what separates us. So let's talk, before I go to that, let me say that often people ask me, well, what has science taught you about God? The biggest lesson is that don't put God in a box. We can't even put the cosmos in a box. The cosmos is more mysterious than we can ever wrap our minds around. There's a big caution here, there's a great temptation, I know, to want all the answers, to want to be able to fit things together, knit them together, and to want to make the divine conform to our limited ways of thinking about the divine. I would argue that that could be considered, to glomming onto a model of God as sort of the ultimate expression of God, could be considered a form of idolatry. Just going to throw that out there. A few of the many currently unanswered questions. Are we alone? I first want to note that the definitive answer of yes is not possible. The universe is too big. Not only is it expanding at an accelerating rate. We will never be able to say definitively there's no other intelligent life or civilizations out there. The best we can do is either discover life elsewhere or say we're effectively alone if it turns out that life is very rare in the universe. We don't know the answer to any of these questions at this point in time. How frequently does life arise? How frequently does intelligent life arise? We're not by any means the only intelligent species on our planet. There are quite a few intelligent species. We are, I think I'm safe in saying this, the only species on our planet that has developed symbolic language to a degree where we can ponder some of these questions, where we can create technologies that we can actually use to explore worlds beyond our own. There are tool using other animals on our planet, and maybe even symbolic language, but this is a big question. How often does intelligent life develop into civilizations? How long do those civilizations last? So what are the prospects for actually communicating with extraterrestrial intelligence? So I want to end kind of on a similar note where I began, an expression of awe and wonder. So will comparative religion with extraterrestrial intelligence ever be possible? What I mean by that is, will we ever discover life with whom we could have deep communication on these very deep, probing, existential questions that human beings have thought about for millennia? Well, I don't know. But this woman here 100 years ago, Alice Meynell, thought that that would be possible. She's a Roman Catholic mother of 8 and prominent suffragette. And 10 years before the first pulp science fiction about travel to another planetary system, she wrote this remarkably beautiful poem called Christ in the Universe. I'm not going to read the entire poem, but I do want to read the last 2 stanzas. But in the eternities, doubtless we shall compare together, hear a million alien gospels, in what guise he trod the Pleiades, the lyre, the bear. Oh, be prepared, my soul, to read the inconceivable, to scan the myriad forms of God, those stars unroll, when in our turn we show to them a man. For Alice Meynell, the thought about the universe being populated with other civilizations was not threatening to her faith. In fact, she welcomed cosmic neighbors. And I think this poem nicely expresses the tone we began on. So with that, I'm going to end up. I'll leave this up here in case people want to read the rest of the poem, and we can take questions now. Thank you, everybody.
Fascinating. I know there are lots of questions bubbling up out there, so send them forward to Linda and Reggie, and as they're being collected, I will ask a starter question, giving them time to sort through a bit. And
don't forget, if you have to leave and you're interested in the Zooniverse, pick up some materials.
thank you. Yes, so for a starter question, you have been in this religion and science dialogue for some years now, and I basically just want to ask why. Why do you think this is so important? And what do you say to people who might say, well, religion and science can't have a dialogue. They're in conflict with one another. How do you respond?
So your question has several parts to it. One, how did I first get interested in this? You know, science evokes a lot of questions that are beyond science's capability actually to address. And I think the same I think the same questions, or not the same questions, but the same feelings that inspired me to go into science also inspire me thinking about science in the larger context of meaning. The question of meaning is important to everybody on this planet, and the culture wars that pervade our society, we need to do something about that. So I'm coming at this from two sides, right? So as a scientist, I want to see a scientifically literate public. I think that that's very important. I think science literacy is really important in making some big policy decisions regarding science. But I'm also coming from this as a person of faith. And yeah, I'm a lifelong Lutheran, but there's actually, that took a number of twists and turns. I did divert from that path for a number of years and was actually brought back by my friends at the Vatican Observatory. So as a person of faith, I also get upset when I see religious views, when I hear dialogue that pits the best science against what I would call kindergarten theology. This is all too frequent. We take the deep scientific views of the universe and we basically pit that against a level of thinking about some of these questions that you would expect a child of 7 or 8 to be at. So I do want to see a fairer depiction of religious thought. I think some of these questions of meaning are very important. And I also would like to see, I acknowledge that there are a lot of people who are hurting in life, who think that science has destroyed meaning, and I would like to see that rectified. I personally know scientists of all different religious persuasions and none, and I think it's very important that people see that there is not just this one option. And also to rectify some of the misconceptions as to how science and religion have interacted historically. This warfare model is just not a good description of the history of religion and science. For most of history, it wasn't like that. There was a lot of give and take and discussion among different branches. So I think that sort of addresses, Anna, you're going to have to remind me the second part of your question, because you asked about how I got interested in this, and why I think it's important. So it pains me both to see people think that science has destroyed meaning and they're living a life without meaning, and it also pains me to hear that from both sides of the equation here, to hear that science and religion can coexist. That hurts everybody. It hurts science and scientific communities, it hurts religious communities, it hurts everyone. So I think that these discussions, I would go out there to say that these discussions are priority one today, that they have to happen. Thank you.
We need to mic the question so that it can be simultaneously translated. So the question and...
Is this thing on?
Reggie, there's another mic up there too.
We're good. We're good.
Okay.
One that's, I'm going to get into some more complicated ones later, but one that's very definitely up your alley. Can you say a bit more about heavy elements that, as you mentioned, are actually formed in stars, and how do they end up in us?
So basically, in the early universe, the only matter that existed, the very early universe, was hydrogen and helium. Pretty much all the heavy elements, and by the way, this is a joke among astronomers and chemists. To an astronomer, everything heavier than helium on the periodic table is a metal. Now, clearly that's not the case for chemists, but that's we call them metals. So these heavy elements are fused together in the tremendous pressures and temperatures at the cores of stars. And it's because the most massive stars explode at the end of their lifetimes that these elements are seeded throughout space and can be incorporated in subsequent generations of stars. I told you that the sun is a third generation star. The sun formed after there were already a lot of metals produced in the universe. So we need those metals, metals in air quotes, for life, for the elements that lead to life. Now, it's interesting that these massive stars, during their lifetimes, they fuse elements as heavy as iron, and the elements that are heavier than iron on the periodic table arise in a couple of different ways. One, when these stars explode as supernovae, there are pressures and temperatures that are reached that can synthesize even heavier elements than iron. So there are a few different ways in the universe to build up these heavier elements. Okay, yeah, I don't want to spend too long on any questions so we can get to more questions.
Okay. This was from a student. Are there things we can understand about taking care of our planet from studying others?
Oh, well, that's actually a great question. I almost think about that in reverse. Are there lessons that we learned in the poor way we've taken care of our planet that we don't export elsewhere? We certainly learn a lot of things about how our history on Earth developed by studying other planets in the solar system, how conditions on Earth were formed over time, just like the other planets, Mars. But because of the human presence on our planet, it's really difficult to... We can only see how humans have impacted our world at this time. So we can't really speak about how other worlds can give us a lesson about how to treat the Earth, because we've already had such a big impact, if I'm understanding that question correctly. But studying other worlds and studying the formation of other planetary systems can certainly tell us a lot about the processes we think were important, were critical in bringing about our own solar system.
So I've got one from a student who asks, so we're seeing here how science can influence our understanding of religion and God. Is the opposite possible? And how do we avoid giving science the kind of absolute description and the
So that's also a great question. I will say this, there are a number of scientists who have been inspired by their faith. That for sure is true. Throughout history, and I think the kinds of questions that might interest us can be influenced by our faith. But I think the danger is here. So let me say right up front that one of the things that I've been party to over the past 20 years are lots of discussions that try to use science to either prove or disprove the existence of God. And they all have one thing in common. Arguing the dialogue partners have already made up their mind through other ways of discerning whether or not God exists, and then they argue the science based on what they believe in the first place. And that's not how science operates. And I would ask you folks, would any God that science could actually discover actually be big enough to be worthy of calling God? I mean, seriously, really. So I would say that our religious views can certainly impact the questions we find interesting to study. And I certainly think we can benefit from the wisdom of the religious traditions, what they've passed on, the way they've thought about God down through the ages. So I think these from that aspect of things, it goes the other way as well as science.
Great question. Here we've got several questions that can be summed up in this one question here. They're about the Goldilocks zone. Just a straightforward science question. Is it true that 1 inch closer to the sun, we'd be consumed, or the opposite, 1 inch further away, we would freeze? Just
No, you know, those boundaries are certainly not that constraining, and not that tight, and there are a lot of things that we have to think about when we think about being in the Goldilocks zone. So we are warming our planet. You know, we are also, the sun is also getting brighter in time. So that so-called Goldilocks zone does move out, but that's happening over a billion years time period. Okay, that's happening over much longer time scale than human impact on our planet. The Goldilocks zone also is determined, or the habitable zone, by a lot of different factors. So at the simplest level here, we look at where the temperatures might be right for the existence of liquid water from the star. But the properties of the planet itself are very critical in determining whether or not life could actually exist on that planet. So there are a lot of things that the 1 inch, no, no worries there. 1 inch is not gonna impact things. No.
One more question.
So I have to decide whether to ask you a science one or a theology one.
Well, okay, so to be fair, right, I am not academically
Right.
trained as a theologian.
So I think I'll go with the science one. And this is potentially something very simple, but maybe a few people are wondering this. So the question is, you know, you showed us a diagram of the Milky Way as a spiral galaxy. Can we even see the other side? Surely we can't.
I'm glad you asked that question. So let me go back to a couple of different things. I know you can't see this in the back of the room, but you know, I talked about the pink and red stuff. That's these gas clouds and dust clouds. This blue background is not a blue background. It actually breaks up into little pinpoints. There's a little blue dot. Those are stars that we can actually see in infrared wavelengths penetrating all the dusty places in our galaxy that we couldn't access with visible light telescopes. We can use radio telescopes and infrared telescopes actually to map out the structure of our galaxy. And that's where this inference comes from. In this presentation, unfortunately, I didn't include an image of a beautiful galaxy called the Whirlpool Galaxy, which really, really highlights some of the features that we see in our galaxy. So this dark band, Milky Way, in this view here, I don't know if you can see, but in the spiral arms, there are all these dark features that are these dark, dusty clouds that we can map them, we can see them at radio waves. And so we can map the structure of our galaxy using infrared and radio telescopes. You're absolutely right. We never see our galaxy like this. We can't. We can't travel outside of it. But we can make measurements from within that tell us the rough structure of our galaxy. And that rough structure is spiral in shape with a bar. It's classified as a barred spiral galaxy. And this is also produced through wonderful gravitational interactions. Give these structures like this bar here. So that's a great question. Thank you, Linda. Yeah. Are you sure you want to wrap up?
No, I could go on. I think we probably should, as class must continue. I see. I'm not speaking.
There's a hand waving back there.
I think we'll talk to you right after. Grace is she's graciously agreed to meet us out there right after class for a few minutes. Very, very few. Classes are actually in session right now in this room. This is class. Reggie's class, Intro to Ethics, and my class, Intro to Theology, are, as part of the grant, being redesigned for science engagement. So you've been to class tonight. And after the break of 10 minutes, we will reconvene in class so that we can debrief this a bit more. T300 will meet in here in small group discussions, and 101 for E300. The other announcement, if you enjoyed this, and I can tell that you did, please be aware that we are having a second science event coming up April 25th, when Ron Cole Turner from Pittsburgh Theological Seminary will come and talk to us about the human future. He's going to engage the ethics around human enhancement and the technologies that we're encountering. And now I want to close with a deep appreciation for the presentation from Dr.